Hello there. We are going to look at one-way ANOVA models. Um, yes, with two groups and with more than two groups. So previously we looked at t-testing, and t-testing you're restricted to two groups. ANOVA is another way of comparing means, but it allows us we can compare two groups, but more importantly we can compare more than two groups. Um, Initially, we'll look at just two groups so you can sort of compare and contrast with t-testing. Okay, so um, moving along, if we could. Right, okay. Um, so, yeah, what do we want to do? We want to sort of try and illustrate the use of sums of squares for comparing group means. We'll show the output uh, from a jump one-way ANOVA. And we'll think about the differences with one-way ANOVA and the two sample t-test. Some of these things we'll do in our actual class, but for the purpose of this micro lecture, yes, let's move through. Sorry. Right. Okay. Sorry about that. A few AV technical issues, but I've fixed them now. Alrighty. So, ANOVA, it stands for analysis of variance. So it all comes down to this concept of variance. Variance in relation to generally a mean. Whether it's the mean of the whole data or the mean of the specific groups within our sample, the idea of variances is critical. So it's the spread of data either side of a mean. Okay, and given that we're comparing means, that's an important idea. It's an important thing to think about. So um, let's move on. Let's look at an example and think about what variance is. So this is just two groups. Okay, there's no real context here. We've got group A and group B and the response. Um, and the responses are, you can see the range of responses here. Now we've got two groups, and in that sample, you can see that the overall of all the six observations from 1 to 4, 7, 5, 8, and 11, you see they all, if you add them up, they add up to 36, and if you divide that by 6, you get 6. So there's the mean of the overall group. All right, so that's kind of a baseline by which we measure the strength of our model. Now, we're suggesting here that whether you're in A or whether you're in B, that has an impact on these responses. Okay, and it kind of, from this very small sample, you could argue that although the sample means are different, see, the sample means are, in this case, actually 4. See, 1 and 4 and 7 is 12 divided by 3 equals 4. 5 and 8 and 11. So that's 24 divided by 3, which is 8. Okay, so there's the mean there. So we've got two different sample means. We've got a spread of data either side of them. So one of the observations is right on the mean, and in this case it's right on the mean as well, but the other ones are spread either side. So in answer to the question, does this reflect, is there an actual difference of means in the population? It's not that clear. You'd have to do a test, really. For the record, I have tested it, and we can't reject the null hypothesis. There isn't. In that sample data, as you see it there, it doesn't give us enough evidence to reject the null hypothesis. Anyway, consider these guys. So the group means are the same. The group means are 4 and 8 again. But you'll notice that, see, the variance is smaller. All right. So what we call these the difference between the model that we're looking at are the means of the groups, and they're both the same in each case. However, the difference between these groups is the variance. Okay, so with this example here, we can see, well, I would say more emphatically, we can see that there probably will be a difference in the population means, given that this is what our sample, and it's only 6, this is what our sample threw up. But because the variance is so much smaller, okay, that gives us confidence. And statistics backs that up. If we do a test, which I'm actually going to show you the output from, then you'll see that in this case, we can reject the null hypothesis of equality of group means, of population means, given the sample and the variance and so on and so forth. Right, so we're going to get to that jump output in a moment. The next few slides are, I'm going to go through them. I would suggest you follow along with me. Don't worry if it gets a little bit confusing and doesn't make total sense on the first pass. This is one of those concepts we really need to thrash out in the lab sessions or the lecture sessions or whatever lessons we have. We really need to just thrash them out together, and you guys need to ask questions. It just seems a little bit odd at first when you hear this, so but I'm going to go through it anyway. But the key take home, if you take home nothing else, is just, I hope you can sense that having a group with a smaller variance leads to more confidence in these means being different in the population than having a big variance like that. So that's really, really important. Okay, moving along. So first of all, we calculate the mean response. You can see there, it's just all of the values added together divided by 6. That equals 6. So that's our baseline. So by the way, we're calculating for these sort of small variance groups here. Now, what do the total sums of squares represent? So it represents the difference between all of our observations and this overall mean, this baseline mean. Okay, so this represents for us variation from both groups having the same mean. If both groups had the same mean, then that line would go right through the middle of both groups. We wouldn't have a difference of means. We'd have nothing. However, if we're trying to test that these groups have different means in the population, we measure it against that baseline, that sort of baseline mean in the middle. So we add up, for example, 3 minus, well, we'll go from the top because, I don't know, we'll do it the way they've done it. 3 minus 6, which is this observation here, minus the mean. Now, and then 4 minus 6, and then 5 minus 6. Now, the reason they're squared, if we didn't square these values, they would all add up to 0. Okay, and do it yourself, work it out. This is classic. It's ever been this. This is the way we calculate variance. We square the differences, or square the, and then we sum the squares. Okay, so we square the differences, then we sum the squares, and it gives us this value of 28. Okay, so that's a value of 28, which I hope makes sense. So 3 minus 6 is minus 3. To the power of 2, which is 9 plus, and that's 4, and then 1. So yeah, 9 and 4 and 1 is 14, and likewise you've got the same variance here, so they all add up to 28. In a sense, what the actual value is you don't have to dwell on it too much. It just is what it is. It'll be different for different data sets. All right, moving on. So what do the errors mean? So errors called residuals. So given that our model, see that this represents our model, the mean, which is the group of the group mean of A is 4 and the group mean of B is 8. That's our model. That's what we're saying. Now, everything which deviates from that mean is an error. Okay, and you expect errors. Okay, so for example, 5 minus that one there's 5 minus 4 equals 1, and 1 to the power of 2 is 1. Alrighty. So, and this one, 4 minus 4, it's 0. So you get 0 to the power of 2 is 0, and then 3 minus 4 is minus 1. Okay, so you get minus 1 to the power of 2 equals 1. So effectively 1 plus 0 plus 1 plus 1 plus 0 plus 1 equals 4. So that's the error. That's what we can't explain. Our model is not clever enough to explain the variation. But you know what? That's okay. That's the nature of this model. But these variations from the group means are the variance within the groups. What we call the variance within the groups. And then what we've got here, the model sums of squares. Okay. That actually indicates the variance between the groups. Okay. So we've got, and the reason that is because you can see here the model, which is effectively the mean, 4, the group mean is 4 and the group mean is 8 there. So we're just saying that minus the overall mean 3 times. Okay, that's our model. That is our model. So, and that, what we have there is a value of 24. Now, again, it's just, it does take a little bit of thinking about. So you're just saying that's our model. We've already accommodated for the errors. We're now just we're looking at the model here, and the model is just basically the group means minus the overall means, and that gives us a sense of the variation between the groups. Okay, so whereas this was the variation within the groups, that's the variation between the groups. So for us to have a stronger model, we want a bigger variation between the groups and a smaller variation within the groups. So there's the output. So there's the ANOVA output from that particular model there. And if you would, this is again this analysis of variance table. There's our sums of squares as we walked out to 24. There's the error sums of squares, and there's the total, which is 28. We've just worked that out in the previous slides. Yeah, or did they go that way? I don't know which way I'm pointing. So this is just an expression of our model. Now, degrees of freedom is, we'll see how that's calculated. It is a little bit of a strange concept. However, in this case, the degrees of freedom for our groups, we've got 2 groups, so the degrees of freedom are 1. There's only sort of one sort of, I guess, interaction going on there in terms of that variable. The error, these guys here, that's the degrees of freedom. There are more degrees of freedom. There are more interactions here, and it adds up to 4. Don't worry about the specifics of that. But that mean square is basically 24. The sums of squares divided by the degrees of freedom. Likewise, the error is the error sums of squares divided by the degrees of freedom, which gives you 24, then 1. Now the F ratio, so this is an equivalent of the T statistic, is basically just that the mean sums of squares divided by the error. Okay, so the mean square for the model divided by the error. So that's the ratio. 24 divided by 1 is 24, which translates to this fairly high, fairly low p-value, which means we're fairly confident we can reject the null hypothesis. All right. Out of interest, what this R squared, this represents the how it's termed is the variation. We can explain 85% of, we can say 85% of the variation in the value, okay, in the response, is explained by these sample groupings that we've got here. All right, A and B. Where do we get 85% from? That is basically 24, which is the model sums of squares, divided by the total. Okay, so there's variation in this scenario here. We're saying that 24 of it, or 24 out of 28 of that variation, although 85% is explained by our model. So there we go. This is something we need to thrash out in class. And there's the ANOVA table. So you can, in the notes, it gives you this mildly scary set of equations here, but you can actually work it out. I'm not going to do it now. Because I think it will kill everybody, and I'm already on for 17 minutes. I better hurry up. But if you can look back through the calculations, and then you should see if you can make sense of that table. However, you don't need to. If you just want to pass that by, that's absolutely fine. Just be aware. Just try and get a sense of what the table is trying to tell you. And in the end, if you just interpret the p-value and interpret R squared, you're doing well. Okay, that's a good thing. It's just, I'm not asking you to, in your assessment, for example, to explain how each of these are calculated. I'm just think it's useful to be aware of it. But if if it still doesn't sink in, so be it. All right. Model sums of squares describes which of the following? So, have a think. The model sums of squares, the variability between the groups, the variability within the groups, the variability explained by the grouping variable. So, there's two answers are correct there. So the variability within the groups is the error. That's the spread within the groups. Oh. Yes. So the answers are A, the variability between the groups, and the variability explained by the grouping variable. All right, I appear to have deleted the answers, but never mind. I like this video. It's about 10 years old, but this is a nice description and much shorter than this video, which gives a couple of examples, which I think it does well. So please, if you get time, have a look at this. It's only 5 minutes, I think, as opposed to mine.
Let's say you want to find out if the beverage that people drink affects their reaction time.
David Eisenberg.
So you set up an experiment with 3 groups.
Okay, let's move on. Oh, there it is. Okay. Right. So, just again, the two sample t-test or ANOVA, when you've got 2 groups, the two sample t-test, you can have multiple tails to test for greater than or less than values, but you don't get, you can't report on, or you don't get the R squared, which is, I think, is a useful assessment of the strength of the model as well. And it doesn't produce a model per se. And also, t-test can't be used for multiple groups beyond 2. All right. Right, now, the assumptions. They are, in a sense, there's a subtle difference between the assumptions of these types of models and for t-tests, which it claims not to be a model. So the variance of the groups is the same. We test for the variance of groups. Remember, we did that using Levine and O'Brien and all those guys. That's exactly the same. All right. So that's the same as we did for the t-test. The normally distributed normal distribution is not of the raw data anymore. Okay, in this case, we do the normal distribution of the errors. Okay, remember the errors that we looked at before? We did the sums of squares of the errors. It's that instead, and there's a way of doing that in SASjump. It adds in a few extra steps, but yeah, it's the error of the the errors within the model that we test. Let's do that in class. I could do it now, I suppose. Right, yeah. Should I demonstrate? Yes, I suppose I could. Okay, let's stop this video now, and I'll jump in. Oh, well, yeah, no, let's stop it now. Let's stop it now, and we'll jump into something else. I just got to figure out how to stop the thing. Ah, yes, there it is. Right. Be with you soon.